I'm happy to be sharing some new work that I've been doing with my student Germano and my postdoc Matteo. So this one is about offline learning. I mostly work in online learning and regret minimization. So this is a bit of a change of speeds for me. But the short story that you're going to be hearing today is how to deal with importance weighting estimators and what are the correct concentration inequalities to use when you're dealing with importance weighting estimators. Well, you're going to see what this means during the slide, hopefully. So this is the rough outline. I'm going to get you motivated about this problem setting that we are looking at, which is called offline learning in contextual bandit problems. And we're going to be talking about specifically the class of importance weighting algorithms. And I'm going to talk about one big issue with these important weighted estimators that are being used in this literature. And specifically the problem with them is that they have very, very heavy tails. And they're just stereotypical heavy-tailed random variables. And as such, it's always hard to deal with them, and it's always hard to come up with the correct concentration inequalities and analytic tools to deal with them. So I'm going to show you how to do it wrong, I suppose, first, and then I'm going to show you how to do it right with a tool that I call implicit exploration, and then I'm going to show you some results. But first, let's get motivated. Right, so let's get motivated. I don't know how motivating this picture is, but this is a very stereotypical data science setup that we see in this day and age. Just imagine the following situation. You're running a recommendation engine. You're building the terminator that is going to feed you ads, right? You're a poor user. You go on the internet, you click, and you see ads and ads and ads, right? And then there's this company that wants to make money by recommending you ads based on your browsing history, based on your preferences, and so on. So specifically, a user comes, you look at the cookies of the user or the context or everything that you know about the user, you serve them an ad according to some recommendation policy, and then you get some reward, which is associated with whether or not the user clicked on your ad. So the problem setup that we are looking at today is, well, just imagine that we have a bunch of data that was generated like this by some behavior policy, some deployed system, and then you want to run a procedure that I call offline learning, and then you want to produce a better terminator that is going to make more money for the company, right? But there's another example that I like a little bit better. So if you attended the talk of Philippe Peu yesterday, he was talking about applications of bandit and reinforcement learning techniques for sustainable gardening. So you can imagine that in such a recommendation scenario, sort of instances about which you need to make recommendations would correspond to plots of land with certain properties. The recommendation that you need to make is about what sort of plant to plant in this plot of land. And then your goal is to maximize growth and maximize love, right? So, okay, I guess this is a bit of a more inspiring example. But I still like this ad example because it's very easy to think about and very easy to understand the context of it. All right, okay, so formally this is the setup that we're going to be looking at. It's called the contextual bandit model. It's a sequential, it's just an interaction scheme between a learning agent and an environment. So what happens in each round is that the environment gives you a context xt that is drawn from some distribution nu. So these are the characteristics of the user, right? Cookies, whatever. And then the agent is going to observe this xt and it is going to take an action at, this is a recommendation, and then you're going to earn a reward, which is some kind of a function of the context and the action plus some noise, right? And then your goal in this setup is to consider a bunch of data that was collected according to some policy, right? These are triples of context, action, and reward. And what you want to do is, based on this data, find a policy that maximizes value, right? Value of a policy is simply the expected reward that the policy gains on expectation with respect to the random context x. And the policy is just a distribution over actions given states, right? So you'll be given a set of policies in which you want to be searching for the optimal policy that gains as much reward as possible. All right, and so what sets this problem apart from a regular supervised learning problem is the fact that the reward that you observe is only associated with the action that you take. So you never know what would have happened have there been a different action logged, right? So if the behavior policy would have sampled a different action, you never know what the reward would have been there. And this is in contrast with supervised learning, because in supervised learning, you typically have labeled data with pairs of x's and y's, right? And you always know what is the loss associated with each possible action and with each possible labeling, right? So this is the key challenge in this problem, this partial feedback aspect of the problem. All right, so these are the assumptions that we're going to be making. We're going to assume that the rewards are bounded in 0, 1. This is a very natural assumption. Just think about clicks again, right? Whether there's a click or not. We're also going to assume that the actions in the data set, they were sampled according to some fixed policy. And we assume that this policy is known. I'm going to call this the behavior policy. This is a bit of a strong assumption, but we're gonna fly with this. So I'm going to use mu of a given x to denote the probability that action A was sampled conditionally on the fact that X was the context. Okay, so this is the behavior policy, and in the setup that we consider, we're gonna assume that we don't know the reward function and we don't know the distribution of contexts. All that we know is the behavior policy. Right. So like I said, our goal is going to be to produce a policy that's good, that has high value, but the way that we're going to be measuring the value, measuring how well our algorithm is doing is going to be in terms of regret or excess risk. And this is defined as the gap between the value of the policy that you output. This is pi hat of n. This is the policy that you're going to be producing at the end of the learning process. And you're going to be comparing this with v of pi star, which you need to think of as the value of the optimal policy. Basically, what we're going to try to do is provide a bound on this quantity against some comparator policy v pi star, right? So we want this quantity to be small. We want the gap between the value of the optimal policy and what we output to be as small as possible. And of course, in this setting, it is natural to expect that we're going to be able to have better guarantees if the behavior policy mu is close to the optimal policy, right? So if the data that we have covers the optimal policy well, then we can expect to have better guarantees, as opposed to the case when we have very little data that comes from actions that the optimal policy would take, right? So we're gonna aspire to have better guarantees against policies that are better covered. Right. Okay. So a standard technique in this literature, there are many different branches, but this is the focus of this talk, is when we use unbiased estimators, so the reward function, and use these for selecting our policies. So a very useful estimator that many people use in this literature is this thing that is called the importance weighting estimator or importance weighted estimator. So what this one does is that it looks at the entire data set and it takes a weighted average of the rewards to estimate the value of some given policy pi. And the weights associated with each observed reward is going to be the likelihood ratio between the policy that you're trying to estimate and the behavior policy. So you're reweighting all observations by how close the action is in terms of its probability distribution to the behavior policy, right? So you just look at, you just weight each observation with the inverse probability of having observed this action, and then you multiply it with pi, the thing that you want, right? So this is well known and well studied in a variety of contexts, and what you can easily show about this estimator is that it is unbiased, and which is good, right? So this suggests that this should be a useful estimator to work with. So no matter what policy pi you're trying to evaluate, the expectation of this estimator is always going to be the true value. So that's cool. But one problem with it is that it has huge variance and very, very heavy tails. So why is that? So basically what can happen is that, so what this, the way that this estimator gets unbiasedness is by dividing with the observation probability, which means that if this observation probability was very small, then this value estimator is going to return a huge value, right? Because you're going to have like 1 over a tiny probability. So with some tiny probability, you're going to get something that is really, really big. And this is really a key characteristic of heavy-tailed random variables. This is pretty much the definition of heavy-tailed random variables. So let me just illustrate what happens in this simple computational example. So the result that I'm going to show you is the result of an experiment with in a contextual bandit problem without context. So this is just a regular bandit problem. We have 100 actions, and the way that the behavior policy and the reward function are set up is that the behavior policy takes actions with small indices with very small probability, and it takes actions with high indices with very high probability. And also the reward function is such that it is very low for low and high indices, but it's high in between. So if we gather some data according to this behavior policy and build our importance weighted estimators, then this is what they look like, right? So the blue dots, they're the true rewards of each action, and the red dots, they're the importance weighted estimators. So like I said, actions with low indices are taking a very low probability. So once they get sampled, the associated importance weight gets super, super high, right? So the way that it works is usually your estimator for these actions is 0, right? So these are all the actions that were never sampled in the data set. But the ones that were actually sampled, they are being compensated with a huge importance weight. So as a result, you're gonna get these super, super heavy tails and these ridiculous estimators of these rewards that are otherwise known to be small, right? So this doesn't really look like a very useful way to guide off-policy learning, because in particular, if I use these estimators and if I simply take the policy that maximizes this importance-weighted estimator, then that is the action that I'm going to be taking, right? So that is the action that has the highest predicted value. And if I just greedily pick it, then I'm going to be picking a pretty bad action, right? So somehow it feels that, that if I just go ahead with these importance weighting estimators, and I use them for policy learning, then I'm basically just overfitting my policy to just random sampling artifacts, to undesirable features of these importance-weighted estimators. So these heavy tails of importance-weighted estimators really causes very serious problems in this off-policy learning setup. Right. So let me show you how people deal with this usually. One typical solution is to say that, okay, I'm going to make sure that I'm going to avoid these sampling artifacts by not really trusting the policies for which I expect to have very high variance and very heavy tails. Okay, so concretely what we do is do a bit of uncertainty quantification of these estimator. So, for example, come up with a confidence bound on the value estimates. So find a function Bn of pi, right? So this is something that is going to quantify the uncertainty of my estimator for policy pi. And let's say that I managed to prove that, that the estimator V hat n of pi is at most Bn pi away from the true value, right? So this is a confidence interval for the value estimator. And then let me just take the lower confidence bound as my estimator for the value of the policy, and then just select my policy accordingly, right? So I'm going to adjust my value estimate pessimistically. I subtract this penalty. So if I have a huge uncertainty about a certain policy, then I'm going to penalize it a lot, right? And then if I have small uncertainty about the policy, I'm not going to penalize it as much. Oh, right, so n is the sample size. Right, yeah, because we're going to be looking at how well these behave as a function of the sample size. Yes, thank you. Right, so this is what I call pessimistic importance-weighted offline learning. So when I came up with this acronym, I was already optimizing for you guys. So I hope that you appreciate my very limited Polish vocabulary. Right. Okay. So let me show you why this is good and why this pessimism is reputed to be a useful way of dealing with this problem. So it's very easy to show that if I select my policy this way, the way that I explained, you do a pessimistic adjustment to your values, then the regret that you're going to be getting is going to be upper bounded by the uncertainty quantifier, the confidence width, evaluated at the optimal policy pi star. So basically, how good your policy is going to be sort of governed by how certain you are about the value estimate of the optimal policy. So somehow, if you can evaluate the optimal policy very accurately, then you're going to have good regret with this algorithm. Otherwise, not necessarily. I'm gonna have some illustration for this, but the way that this is proved is just ridiculously simple. So you just use the fact that v pi hat of n, the value of the policy that you output, is lower bounded by the estimated value minus bn. So this is just the definition of v hat and v. And then by the definition of the algorithm, I know that this is higher than the same quantity evaluated at pi star, simply because I picked the argmax of this expression, right? So this value must be lower. But then I use again my confidence bound that says that v hat and v are at most b away from each other, right? So I pick up another b at this step of the analysis, right? So this is the way that this is proved. I call this a folklore theorem. Some papers claim this as a theorem of their own, but I think that's kind of ridiculous because this is, just like a one-line calculation, literally. You cannot really copyright this, right? So if you try to do the same argument without this pessimistic adjustment, then the best guarantee that you can get is going to be the sum of the uncertainty quantifier at the optimal policy and the uncertainty quantifier at pi hat of n and the policy that you output. Right, so let me just go back to this picture and show you what these guarantees look like. So if you do the pessimistic adjustment, then this is the guarantee you get. Then what you get is proportional to bn, the confidence width at pi star, and otherwise it is the sum of the confidence width at the pi star and the policy that you output. Right, so if you put these confidence widths on the picture, so I just put these LCBs on the picture, and you evaluate these thingies, then you're going to see that this green arrow, this is the confidence width for the optimal policy, right? For the optimal action. That is the distance between the LCB and the actual value, and the uncertainty of this bn pi hat n, like the uncertainty on the output policy without pessimistic adjustments, it corresponds to this purple arrow, right? So in practice, this term is always huge because it's precisely large uncertainty that can make you pick a very bad policy. So that is the reason that this pessimism is considered like a good idea here, because typically you get much better solutions with much less uncertainty if your policy covers, of course, the optimal policy well enough. All right, good. So, right. So, in particular, if I follow the pessimistic policy, then that is the action that I'm going to be picking, which also doesn't look as great. But as I'm going to argue, this is really the result of a very poor algorithm design and usually a very poor choice of the uncertainty quantification. So that is one major challenge when it comes to importance weighting estimators, how to come up with correct choices of Bn that is going to result in good policies and tight confidence intervals. Right, so let me show you a typical method of calculating this confidence width. So this confidence width can be defined in terms of this thing that I call the policy coverage ratio. So what this is the sum of the ratios between the policy that I'm evaluating, right? So this is something that is associated with the policy pi, and it is defined as the sum of the ratios between pi and mu, pi the target policy and mu the behavior policy. And what this kind of measures is how far these policies are from each other, to what extent do they not match each other, right? So if there is in particular one action on which pi puts a high probability mass, but mu puts a very low probability mass, then this ratio is going to be huge, because it means that pi wants to sample actions from wants to sample actions that are not really ever present in the data set. Right, so this is what I call the policy coverage ratio or coverage ratio, and it measures the mismatch between pi and mu. And one thing that you can show is a confidence interval of this form. So it's basically an application of something that's called Bernstein's inequality. So this says the following. Let's suppose that the behavior policy is such that all of the action sampling probabilities are bounded away from zero by some constant alpha, which is a very, very strong assumption, right? So basically, it means that every action was sampled many, many times in the data, and then under this assumption, the confidence width of the importance weighting estimator is upper bounded by something that is proportional to this coverage, right? So the confidence interval is going to be wider if your policy is poorly covered and thinner if it's less poorly covered. And well, there's a bunch of extra terms. I'm going to optimize this in a second, but what I want to call your attention to is this extra term in here, which is proportional to 1 over alpha. So typically, this alpha, smallest sampling probability, is going to be really, really tiny, and this part is going to be like really, really huge. So this results often in very, very loose confidence intervals. Right, so let me show you what is the result that you get if you apply this concentration inequality. It is going to give you a regret bound that, of course, has the bound evaluated at pi star, right? And if I optimize this tuning parameter beta, which is a parameter of the confidence interval, then I get this result. Okay, so I think this is probably the most readable version of this result. What it says is that my regret against policy pi star, the optimal policy, depends on the coverage of pi star, so how well pi star is covered by the behavior policy. And it goes down at the rate of 1 over square root of n. There's also this dependence on the log of the cardinality of the policy class that you're working with. I'm going to talk about how to relax this result that currently only works for finite policy classes. But what's nasty about this bound is that this 1 over alpha shows up in here, right? So that this second term just blows up to infinity if there is only a single action that was sampled with a small probability. And this and notice that this lower bound needs to hold for every single x and every single a. So for every context, even contexts that were never even seen in the data set, right? These action probabilities need to be bounded away from zero, and that is typically never true. This is typically like exponentially small or even zero in most applications. So it's in my opinion, it's just completely unacceptable to have anything like this in a regret guarantee or in a concentration bound. And actually, I did not cherry pick this result from the literature because every single paper written on this topic uses the same type of concentration inequalities and makes the same type of assumption and ends up with a 1 over alpha in their guarantees. Right. So let's think for a second about what goes wrong and why it is inappropriate to take this approach that I was suggesting in the previous slides. So if you look at these estimation errors, like the estimation error is the difference between the blue line and the red line. So what do you notice about these? What do you notice about the behavior of the tails? So like I said, this is a very heavy-tailed random variable, right? But let's consider separately the upper tail, right? So the deviations that go up, right? And the lower tail. Do these behave similarly at all? Right, so they behave extremely differently, right? You see that it's only the upper tail that is heavy. You only see very large outliers in the positive direction. You only see very radical overestimations of this importance weighting estimators. But they are, the smallest value that they can take is 0, right? So the lower tail is very thin, right? The lower tail is always nicely controlled. These differences downward are always very small. But the differences upward, they can be ridiculously large. And they get larger and larger as the sampling probabilities get closer and closer to 0. So the tails are just ridiculously asymmetric. The upper tail is much, much heavier than the lower tail. And as such, it is hopeless to have symmetric control of the deviations, right? You have seen that this Bernstein's inequality that you are using to control the fluctuations, it was a two-sided confidence interval that was symmetric, right? But it is obviously the wrong tool for working with this kind of random variables that have asymmetric tails, right? Because your tail estimates are going to be like hopelessly conservative on the positive side. So, so the point that I want to make is that that this is not the right tool to be working with importance weighting estimators, and this is the takeaway message that I will eventually try to convey once I get to the correct way of doing things. So this is what I consider to be the correct approach. So this is pessimism done right. One thing that is very often used in the literature on importance weighting is just truncated importance weights. So one way to make sure that the tails are not as heavy is to make sure that the denominator in these estimators that you're using is just bounded away from 0. And we can do this artificially, right? So we just want to make sure that the denominator is never too small and the estimator doesn't blow up. So it's very, very common to just truncate these estimators in a way by introducing this max operation. The version that I'm going to be talking about is something that I call the implicit expiration estimator, and that is something that I've been using since like 2015 in a variety of bandit problems, mostly online learning. So it really consists of the following. I just take the importance weighting estimator, and then I just add a little gamma to the denominator to achieve this tail truncation effect. Right, so this feels a bit like a hack, right? It feels a bit like, you know, something that you do when you're trying to debug your code and trying to see what is going wrong, and you are trying all sorts of things, and then you just arrive to this stuff, and it feels like a heuristic. But I'm going to argue here that this is actually the correct way to deal with this problem. I know that this sounds a little insane, but let me show you some support for this. So you can see, first of all, that it is already doing something very similar to a pessimistic adjustment to a value estimate, because you see that the bias that this introduces is a pessimistic bias. You see that by reducing the denominator, right, you're just pulling your estimator closer to 0, right? And since we are talking about positive valued rewards, this means that you're underestimating the reward. You're replacing the unbiased estimator by something smaller, which means that you are being pessimistic, right? You're getting a lower bound on the reward. And what is super nice about this is that this is beautifully controlled fluctuations. This is beautifully controlled upper tails, which is something that can be observed experimentally and can be proved very simply as well. Right, so if you look at the importance weighting estimator, this is just the previous figure, just zoomed in a little bit. You know, you remember that there are some red dots over there at the top. So the importance weighting estimator overestimates the value really, really radically. If I do this pessimistically adjusted importance weighting estimator that I discussed previously, and by subtracting the confidence width derived from Bernstein's inequality, this usually results in very, very radical underestimates of the value. I'm actually not showing the entire error bars here, but the error bars on these first few observations are really down in the basement or down in the core of the Earth. I mean, they are like really, really ridiculously large. So this is a very serious underestimation usually. But if you use this importance, what am I talking about? The implicit expiration estimator, then this is the result that you get, right? So this is these are the values that it is going to return. You see that it of course underestimates the rewards, as it should, right? As it says on the tin. But you see that for actions that are sort of well covered, it is a much tighter lower bound than whatever you can derive from Bernstein's inequality. You see that for these actions, it is behaving exactly the same as the unbiased estimator, and it's a very good estimate of the rewards, and it is somehow behaving a lot more reasonably. I'm trying to estimate a reward that is in the interval 0, 1, and this gives me an estimator that is in the interval 0, 1, right? And it is somehow like much more pleasing to look at, and it's something with a lot nicer properties, as we're going to see. Right, so this looks nice. Let's see what we can show about this. Right, so notice that both the upper and the lower tails of this estimator are now nicely controlled. They still behave differently, but in particular, what we're going to show is that if you use the correct tools for the two tails, then you can get very nice guarantees for this problem setting. So let me just check how much time I have. Okay, very good, good. Right. Okay. So let me show you these tail inequalities for the implicit expiration estimator, which, as you will hopefully see, are quite aesthetically pleasing and lead to tight results. So the key quantity that is going to determine the tightness of the bounds is going to be something that I call the smoothed policy coverage ratio. So it's similar to the coverage ratio that we have seen before, except that there is a gamma that appears now in the denominator. So this is expected, but it is also scaled by the reward RT. So this is something that is going to make this coverage ratio even smaller than it was before. Recall that this reward is between 0 and 1, right? So this is again something that is going to pull this ratio closer to 0. So it's very easy to show that the bias of the estimator is exactly controlled by this coverage ratio. It's essentially this gamma times the coverage ratio is the expression of the bias, right? So this is the price that we pay for introducing this little gamma in the denominator. It's a bias that is directly controlled in terms of the mismatch between pi and mu. And it can also be shown that the variance of the estimator is also upper bounded by the coverage divided by the sample size n. Right. So let me show you the two results on the upper tails. Right. So I was saying that we're going to be using two different tools for the two different tails. So the first result, which is from a paper of mine from 2015, which was written in the context of bandits, online learning in bandits. So this is a tail bound on the upper tail of the estimator. So this one says that v hat, the estimator that we get, is never too large, never much larger than its expected value, and it is directly controlled by 1/2 gamma n. Right. So so the larger gamma I set, the thinner the tail becomes, and the better and better uncertainty quantification I'm going to have. But of course, remember that this is a biased estimate. So if I set a very large gamma, then I'm going to be like really, really underestimating very conservatively the value. But notice that this is not looking like Bernstein's inequality or Hoeffding's inequality, because if you use a traditional concentration inequality here to control the tails, then you also get a term that is proportional to gamma, right? So you get like 1/gamma n plus gamma, and then the way to optimize that is, well, you're gonna be getting some horrible terms if you do that. Right. So notice that this implies that the pessimistic adjustment that we wanted to have in our value estimates is already baked into the estimator. The pessimism that is induced by this little gamma in the denominator is already resulting in a high probability upper bound on the values. So I don't need to provide additional uncertainty quantification on this estimator. I don't need to subtract anything else from it in order to make it pessimistic. So this is a very nice bonus that you're getting here. And as for the lower tail, it can be controlled by a concentration inequality, which is again a little bit like Bernstein's inequality, but it does not need the random variables to be bounded with probability 1. So this one says that the lower tail is bounded by the bias, of course, right? So and and the variance, and something by gamma times the variance, and this 1 over gamma term that always shows up whenever you use Chernoff techniques for proving concentration bounds. So if you recall the results on the bias and the variance, you see that both of these terms are of the order gamma times coverage ratio. And notice that there's absolutely no need to assume now that the mu's, the sampling probabilities, were bounded away from 0, because we are talking about the lower tail of a non-negative random variable, and lower tails of non-negative random variables are always tightly controlled. So this is a result that I think is not as well known as it should. This is a bit of like a folklore result in concentration inequalities. It's hidden away as an exercise in this book by Boucheron, Lugosi, and Massar about concentration inequalities. Right, but okay, let me just show you both of these at the same time. So what this estimator then does for you is that it gives you an upper tail bound, which is very nice, right? So this is just 1 over gamma, and the lower tail is controlled by the coverage and this 1 over gamma thingy. So let me show you the result that this leads to, so that you appreciate the fact that these results are so nice and tight. Right. So this is the main result of our paper. It says that the regret of this importance weighted offline learning algorithm using this IX estimator is bounded by 2 gamma times the coverage ratio plus 1 over gamma n. And if you optimize, so if you optimize your gamma, then this is the result that you get, right? So then it goes down at the rate of 1 over square root of n, and it scales with the coverage of the, that should be pi star, I'm sorry about that. So it scales with the coverage of the optimal policy. So this is exactly like the previous result that I was showing, with the exception that there's no additional term that corresponds to 1 over alpha. So we have managed to completely wipe out this assumption that the sampling probabilities need to be bounded away from 0. And we don't pay the price of the smallest observation probability in the bound, which I think is a pretty huge improvement over everything else that has been done, and it has been achieved by using the correct techniques. So let me just quickly walk you through this proof. It's the same argument, or very similar argument as we have seen before. So here, in the first step, you're just using the bound on the upper tail of the estimator. It says that V is always greater than V tilde minus this constant thing that does not depend on the policy. But by definition of the policy pi hat n, this is greater than V tilde pi star, right? Because we selected the argmax policy. But then here we just use the inequality on the lower tail, right? Where we pick up this coverage ratio of the optimal policy pi star. And then this is what concludes the entire proof. So again, what I want to stress is that there's absolutely no need to assume lower bounded sampling probabilities here, and we just completely wipe out this 1 over alpha, which is quite cool. So let me show you. Yeah, we have some extensions that go beyond finite policy classes as well. So these results that I was mentioning so far, they were all requiring finite policy classes, and the cardinality of the policy class was always showing up in these guarantees. You can replace this by things like VC dimension or Natarajan dimension or Rademacher complexity or whatever you want. But but often the details of working out such extensions is complicated. What we also do in the paper is a PAC-Bayesian extension. I don't know how many of you are familiar with PAC-Bayes. This is basically like a fancy concentration inequality for classes of policies. So this is a result that works for infinite policy classes. The output of this algorithm is a distribution over policies as opposed to a single policy. And the policy that this version of the algorithm outputs is what maximizes the importance weighted estimator plus the relative entropy between a prior distribution, P0, and the distribution over policies that are being considered. So this is basically a way of regularizing the distribution over policies in a way that it doesn't get too far away from some prior distribution. And the result that we managed to prove for this is a regret bound in the space of policies. So we get a policy that competes with some optimal distribution over policies with a regret that is proportional to the coverage of this distribution of the policies plus the relative entropy between the prior and the competitor that you're shooting for. And this can be tuned again to achieve like a square root of 1 over square root of n convergence rate to 0. Right, okay, so let me just quickly flash some experiments. So we have run some simple contextual bandit experiments with the algorithm that we propose, just importance weighting with this implicit expiration estimator. We also looked at the clipped importance weighting estimator, which replaces the mu plus gamma by the max between mu and gamma. So that is something that behaves very similarly, as the experiments confirm. And we have also implemented this method that uses this Bernstein's inequality confidence bounds. And right, so let me think which ones to discuss. Okay, so maybe let me discuss these results. Okay, so what happens here is that you have a bunch of curves, and each curve corresponds to data collected from a behavior policy that is becoming better and better and better. So the darker these blue lines are, the better the behavior policy is, the closer it is to the optimal policy. So of course, if the behavior policy is close to the optimal policy, then we should have good regret always. So that is the significance of the darkness of the lines, and that explains the multitude of the lines there. And what is shown on the x-axis is the choice for Ix. This is the choice of gamma. For the clipping estimator, it's also the choice of gamma, and for this Bernstein's inequality based bound, that is the choice of the beta tuning parameter that it has. And what we see here is that well, this importance. So our estimators, they behave like pretty nicely, predictably well. The yellow line is the theoretical recommendation of how to tune the parameter, and we see that that this method works super well for the theoretically recommended rate, and also the behavior of these curves is exactly as predicted by theory. Whereas for this other family of methods that is using Bernstein's inequality, then you don't really see like any pattern to discover there. So basically what that method is doing is that for different realizations of the behavior policy, the algorithm behaves in a completely unpredictable way. It's very incoherent. It's all over the place, basically. And it's also unpredictable whether a small value of beta is going to work for your problem or a large value of beta is going to work for your problem. You see that for some problems, a small value of beta works excellent, right? And these are actually the cases in which the behavior policy is bad. So if the behavior policy is bad, then you're going to have huge adjustments to actions that you have not seen before, and you're going to be picking those. And otherwise, if the behavior policy is good, then this algorithm just doesn't seem to work well at all. So basically, what you can read out from this result, and also these following ones that I'm not going to explain all that much. So basically, I'm just going to say here is that here, what is shown on the x-axis is how much worse the behavior policy is getting over time. So with large inverse temperature parameters, the behavior policy is going to be worse and worse and worse and further away from the optimal policy. And you see that the performance of our method gets worse and worse and worse as predicted by theory. That's what the theory says, that the behavior policy is very far from the optimal one. Then we should be working worse. And this is exactly what happens in the experiments. Whereas with this other method, as the behavior policy gets worse and worse and worse, you see a performance decay, but suddenly a performance improvement as well. And this is just strange. This is not explainable by theory. And basically, what I like about these plots is that, well, if you want an algorithm for which the theory correctly describes its behavior, then you should be picking this Ix or this clipping estimator. If you want an algorithm that is completely unpredictable and does some weird stuff that you are not able to forecast, then be my guest and use this other algorithm. But I would just probably go with the one that is theoretically more predictable. Right. Okay, so let me just wrap up. So the conclusion is that I think that this is the right way of doing importance-weighted offline learning. We relax all the assumptions. The algorithms work well empirically. All the terms in the bounds are smaller than everything else that has shown up before. I did not talk about it, but this algorithm can be implemented efficiently as well, as opposed to some others that were proposed in the literature. But there are many, many open problems. For example, we know that it is possible to put the coverage ratio under the square root. So we know that this improvement is possible. We just don't know how to do this efficiently. We don't know if there are matching lower bounds for this scenario. This is a big mystery in all of offline learning. I can tell you more about that. This is a complicated topic. And of course, a good question is how to extend this to reinforcement learning. This is always a nice open question to address when talking about contextual bandits. But really the technical takeaway is that you should never use symmetrical tail inequalities for importance weighting estimators, which message is probably better conveyed by this little picture here. So you see that just introducing this little gamma in your estimator looks like a hack, right? So it looks like an idea by this guy, right? So that may feel like a bizarre and unpredictable thingy. So people have been thinking about like all sorts of complicated ways of controlling the tails of their estimators by very complicated tail inequalities, Bernstein's inequality, and so on, and doing all these adjustments and coming up with these very complicated, theoretically motivated algorithms. But turns out that in this specific setting, you should be happy with this very simple trick of truncating the importance weights. That works fantastically well. You can actually support this by theory, so it's not always the complicated things that work best. Often, it is the simplest ideas that are most effective. And again, if you're working with importance weighting estimators, never used symmetric tail inequalities. I hope you're going to remember that because the tails behave very differently. And again, also, sometimes the simple ideas are the best. All right, thank you very much.